Hello, good afternoon, everyone. Hello to everyone online as well. If you can't hear me, let Josie know. Josie is waiting. I'll try and speak louder, quieter, whatever is necessary. So hi everyone. My name is Palgrave. I'm from UCL. I'm also the co-director of HarwellXPS. So thanks very much for attending today. I've been here online. It's really great to see so many people coming through a seminar or webinar. We've had some really great examples of XPS usage today. And so I'm sure many of you who maybe haven't used XPS or maybe haven't used XPS for a while will definitely be running out to collect data. And when you do that, you're then going to be faced with a bit of a challenge. So a big part of getting the most out of XPS is not only designing a great experiment to collect data, but it's also doing some meaningful analysis of data to make sure you understand what your data means, try to answer your research question that you had, and try to avoid falling into any of the pitfalls. Let's just see if the monitor is working. Oh. So the pitfalls. The pitfalls in XPS 15. So Simon actually gave a fantastic example at the beginning of this talk of identifying a problem, some erroneous fitting that turned out to be in some published XPS data, and then going ahead and doing some more experiments and actually verifying or contradicting, I guess, their interpretation, finding the real interpretation. In that case, it was fitting gold structure. Unfortunately, that situation is not unique. It's not anywhere near to be unique. In fact, bad fitting of XPS XPS data is rather endemic in the literature. So there's a recent study, I was going to bring it up at the end, but I think it fits now. The reference will come up on the last slide, where a group of XPS experts analysed how well papers have done the job of fitting XPS data from top journals, so from leading journals in chemistry, materials chemistry, buildings and vegetables. And their results are actually quite shocking. They found that for just unfitted data, so when data was presented without any fitting, I think you all know what fitting is, but I'll explain it in a minute. When data was presented without any fitting, there was quite a small number of what they call fatal errors. So fatal errors are errors that completely undermine the conclusions of the study. So I think they got about 4 or 5% of the papers had what they call fatal errors, where they completely messed up their analysis. When people started fitting the data, that number went from about 4% of fatal errors to around 40%, 40% of data in leading journals is analysed completely incorrectly, which completely undermines the conclusions of the study. This is a major problem in our field, and so I'm going to have a run through in kind of a light-hearted way, but hopefully there's a bit of a serious message as well. There is. Things that people might get wrong. So there's going to be a lot of examples. If your data appears here, I apologize. I hope not. That's going to be embarrassing. All right, I promise I would say what p-fitting is. I think all of you know, but let's kind of set it out. So p-fitting, of course, isn't unique to XPS. It's running lots of different data analysis kind of workflows. So p-fitting is building a mathematical model to fit the data. So that's step one. Step two is making physical interpretations for that model. And then you interpret it. And step three, which sometimes kind of people forget, the whole reason we're doing this is we're trying to answer some kind of research question. So we have something we want to know about our material, and so that's the reason that we do the p-fitting first. So there's some examples here. Of course, building a mathematical model in the case of XPS, we're combining the background function, and we see lots of examples of that, and some key functions, and fitting them to the experimental data using an algorithm. That, using modern software, is extremely easy to do. Within a couple of clicks, you can do that on Casa XPS, Talent XPS, whatever your favorite fitting program is, it's very, very easy. Part 2 and part 3, a little bit more difficult. So an example of part of in physical interpretation you might make, for example, the average oxidation state of iron in my sample is 2.5. That might be an interpretation you make from your fitted your XPS fitting. And the research question that might answer, I don't really know much about catalysis, I kind of guess catalysis question. Has the iron been oxidized during my catalytic process? How is people that sensible? Yes. So what could possibly go wrong? Well, that's the rest of the book. Well, so some things that can go wrong just with these 3 steps. So firstly, of course, the model doesn't fit the data adequately. For whatever reason, you mess up your fitting algorithm, you forget to press fit, it happens. Usually there's going to be examples, and so you fail on the first step. It's quite unusual to fail on the first step. Steps 2 and 3 are where the problems come in. So, for example, the physical interpretations are incorrect. So, whatever your conclusions were about the ion oxidation state, for some reason they're wrong. Whatever your conclusions were about the types of carbon, the gold oxidation state, Simon showed that they're just incorrect. And most importantly, that leads to part 3. The research questions that you wanted to answer are answered incorrectly. So that kind of goes back to the quote I had on the first slide, which I forgot to mention, which is a nice quote from a guy called Henry Really Short. He wasn't talking about XPS because he lived in the 1910s. He said, wisdom doesn't come in knowing more that is new, but knowing less that is false. And I think that's definitely true on some of the XPS structure we're going to see coming up now. Okay, so without too much further ado, we're going to have 10 evidences for XPS fitting. In no particular order. I realize I should have done them in kind of sentence, but it's kind of random. Evidence number 1, which is really, really common, especially with people who are just coming into XPS. Whatever your research question is, it doesn't require you to do peak fitting, but you do anyway. So some examples of research questions you might have, which are very, very common when you're doing XPS analysis. What elements does my sample contain? Kind of important, or sample surface. I know I tried to know the catalysis one, so it might be that. I'm not catalysis, but what is the ratio of iron to nickel? But what is the ratio of 2 elements to each other in my sample? How does the concentration of dopant change with etching time? I do some etching, for example, as we saw earlier. Now, in this case, none of these really require you to do any peak fitting. They probably don't require you to do peak fitting. So the elements that your sample contains can be identified just by comparing the peaks to a database of an XPS library, which is included in all popular software. If you just want to compare the total amount of 2 elements, normally, not in every case, but very often you don't need to peak fit that. You can just measure the areas under special algebra and the background function. So you do need the background function, but you don't need to do the full fitting procedure to get that ratio. Similarly, with the concentration, if you're doing etching, you don't need to do this. But often people do fitting anyway because they just think it's something that they kind of should be doing. So what I would say, think about what you're trying to achieve. What is your research? What is the aim of your XPS experiment? Maybe you don't even need to do fitting at all. You can save yourself a lot of time. And you can save yourself from all of these things which are coming up. So there is number 2, fitting broad symmetrical peaks with many components. Okay, so here we start the kind of horror show. No, there's no citations given on any of these to protect the I was going to say protect the innocent, but they're not. So here we have a phenomenon. What I recommend to everybody is to get when they start doing XPS fitting, get a spectrum which gives you a symmetrical peak shape. So it could be a carbon spectrum from, I don't know, just an adventitious carbon or anything, and fit it with 2 components and see the number of different ways you can move those 2 components around, and it will give you exactly the same quality of fit to your spectrum. And here's some examples of this. So I would say that on the try again with the pointer. Yeah, okay. I would say on the left-hand side here we have these different peaks. This is 4F peaks, which are pretty symmetrical, but the authors have decided that there are 2 components in here, and they've decided that the distance 0 component of lower binding energy makes sense. Distance 3 plus there are in this particular ratio, but I can guarantee you could put those in any ratio you wanted, and you will get an equally good fit. So in one sense, it helps your paper. If your annoying referee says, "Well, prove that you have 63% 53 plus," no problem. But you can look at any other percent 53 plus that you want to. So in terms of satisfying referees, it can help in terms of actually finding out about your sample less. So another example with carbon, very, very common. Two components listed here, and again, you could fit those in kind of. So just some tips when faced with broad symmetric peaks, try to bring in other information to aid the fit. So it might be, for example, with carbon, that if you're looking at a polymer, for example, you might know from other techniques, NMR or other kinds of structural characterization techniques, you might know what the different kinds of carbon you have in your polymer are. And so you can bring that information into your picture. So you could, for example, constrain the peak areas to the correct ratio based on your molecular formula, and therefore that will give you a much more robust fitting rather than just allowing the parameters to vary, to any levels. Use realistic forward part maximums, that means a breadth. Based on standards if possible. So if you can measure a standard of pure bismuth 3+, for example, that only has bismuth 3 and no bismuth 0, and then compare it to this one, that could give you some confidence that this peak really is broader. So it might indicate that there is another environment for this. I don't really think it's bismuth 0 instead. And I would say, lastly, acknowledge that many different models will fit approximately. You can't bring in that extra information. It might be that you can't really get a unique fitting that is better than any other. So you might not be able to answer the question that you set up. Okay, number 3, using terrible backgrounds. So there's a few examples of terrible backgrounds here. So I'm going to start with, let's start in the top left. So the background function, as we've heard today, is a function that's supposed to account for the intensity of the XPS peak, which isn't to do with the actual core line, the photoemission, or whatever feature you're looking at. So a difficulty of XPS is often that background changes on either side of the peak due to some. So we have to model that somehow. But what your background function shouldn't do is ever go on top of the data. So your background function can't be more than the data, because that would indicate you have negative photo emission. So in these samples, they're not too bad, but you can definitely see the background is going above where the data is, and in this case here. This one, I think, was applied to this slide. This one was applied to this slide. They've applied a Shirley background here. We talked about different background functions early on. There's lots to choose from, lots to learn there. But hopefully, even beginners would see that there's a little problem here. They've set their Shirley background to finish kind of halfway in the middle of this photo. So you're not really capturing the changing background at all. Your background and your fitting on top of that background is going to be entirely determined by exactly where you place the endpoint. So some tips about when applying the background. I think, as Mark said earlier, Shirley background is a good place to start. There's a lot more kind of physically meaningful backgrounds that you can move on to. I will definitely start with a Shirley background. Background should not go about the data to a greater extent than the topics. There's no visible way that can happen. So try to avoid that situation. If necessary, use multiple regions. You can't get one region to fit across, you can use multiple regions. Position, start, and end the regions well away from certain features. So that's what the people on the top right failed to do. And collect sufficient data, I mean the energy range, either side of the peak to allow proper background fitting. So that's a problem that can happen if your peak is, for example, in the top left-hand side here. I think they probably have just cut that graph off. But if their data ended there, then that's not really sufficient. You should collect more data so you have a nice flat region. Okay, 4 width half maximum and 1 with WTH, what the hell? But I did have a debate with myself. 4 width half maximum. You often see things like this. So here we have an oxygen peak being fitted, and there's 2 components to this fit. One of them has got an absolutely huge 4 width half maximum, and one of them has got a tiny 4 width one. Let's try and make it point to work. You can see what I mean. The top right-hand section there, and likewise the bottom one, the lower one, it's not quite as bad. But 3 of the peaks got reasonably similar 4 width half maximum, and one of them, the gallium one, is really, really narrow. So for most photo emission features, this is not physically realistic. Let's see what we say here. Yeah. So it's all for most. If we're fitting, for example, oxygen peaks or carbon peaks or whatever, there's not going to be that much variation in the forward time maximum. Different environments, like the same. So as a starting point, when you're fitting spectra, I would always use the same forward time maximum. That's the best starting point. It doesn't mean there can't be variation between different chemical environments of the same element, but it's a good starting. Understanding expected forward time maximum of the specific core line. Again, ideally using a standard. So come back to this idea again. It's really useful in to avoid many of these problems to measure a standard. If you think you have a mixture of different oxidation states, see if you can get a sample where you know only one of those oxidation states is there and measure that. And just see what it looks like. If you do both of them, even better. Measure both of them separately, and then you'll understand a lot better what the spectrum look like when you come to fit the combined one. It will be much easier than just trying to work with a single combined system. And understand what factors affect the peak width and what an acceptable range is for your instrument or sample. I expect that this is very large, up to 1F, will be pretty too wide. It must be made up of multiple components, but fitting it as a single component or one very large component. Okay, fitting noise. Fitting noise. This is I should say all of these figures are in published papers. Some of them in journals you would have heard of as well. So here they have some noise, but they didn't want it must be iron. So they fitted iron. Not much to say here. Don't do it. Spin orbit problem. Okay, so this is probably I'd say number 2 biggest source of error. Spin orbit problems. So as we've I think seen in earlier talks, many XPS features here are spin orbit doublets because your orbital has angular momentum and the electron has spin. Those things can come together. So you always have a doublet if you have a E, D, or F orbital. So the first thing that can happen, people can confuse the two parts of the doublet for two chemical environments. I don't have an example of that here. That's not that common because most people get at least as far as reading about spin orbit. So they know that certain orbitals come in two parts. But what often goes wrong is fitting those two different parts, especially when you have multiple chemical environments of orbitals which have spin orbit doublets. It becomes a little complicated. So here we have an attempt to fit some silicon peaks. This is actually a little bit subtle. This is a little bit hard mode. But what they've done here, they've fitted the 2p3/2 and 2p1/2. Those are two spin orbit components of the 2p orbital. But unfortunately for them, they fitted them the wrong way around. So the 3/2, the larger J value is always the most intense. But unfortunately, they put them the wrong way around. They also haven't, I don't think they put them in the correct ratio, even though they reverse the ratio. There's a certain ratio of intensity that the spin orbit component should be, which I'll come to in a second, but I don't think that's been imposed yet. And it definitely hasn't been imposed down here, where we have a tiny little and a whopping rate of 2p1/2. I'm pretty sure they just put some components in there. And we also have some throwback to some earlier problems here with vastly different forward time maximum for NOAA packets. A few more. So this one is not completely obvious when you look at it, but this is some lead orbitals 4p3/2 and 1/2. Now the problem is that the 4p1/2 has actually got a much bigger energy separation than is given here. In fact, it wouldn't even be on this spectrum. So this peak is something completely different because the separation between the orbitals is so big that it would be off the screen. Likewise here, we've got some lead kind of overlaps manganese. It's a particularly challenging example, but the lead 4p3/2, which is now here, is for some reason much narrower than it was in the previous spectrum and in a completely different position. And it also bears no relation to the width or the intensity of the 4p1/2. And it gets worse as we go down. So I think tips for fitting spin-orbit doublets: look up the energy separation. All of the energy separation to every orbital that you'll ever find is tabulated. So find out what that is. There's a very big variation. Some of them are separated by less than an electron volt, so they'll basically be unresolved in most instruments. They'll just be an asymmetric peak. Some of them are separated by tens of electron volts, so they will be what's in the completely different parts of the spectrum. So it's really important to look that up to make sure we're not doing something a little bit. Use the correct intensity ratio, and make sure the higher J values are lower binding energy. So that's important. So for p orbitals, it's always 1 to 2. For the orbitals, it's 2 to 3. For f orbitals, it's 3 to 4. That's the intensity, the area ratio, and not that height ratio. Usually, the spin orbit components have the same forward hub maximum line shape. Not always. There are one example, titanium 2p, for example, where they don't, which might be relevant to some people. But the starting point is to keep them the same forward hub maximum, the same line shape. Peaks are not what you think they are. I know a good paper, but I couldn't find it when I was making this. I don't have an actual example. But misidentifying photo emission features is reasonably common, and obviously can completely derail your analysis and your interpretation. You think you have an element there which you don't have, or you quantify an element completely incorrectly, and it's a much lower value, maybe much higher value. So always consider when you're identifying spectral features, consider what other things could be there. So it could be photo emission lines, it could be OJ lines, it could be some energy loss features. Check this against an XPS library. So when your XPS spectrum comes off the machine, it could have a high resolution region, for example, saying manganese 2p, as we saw earlier. That doesn't mean no other peaks can be in that region. That's just the label that the XPS machine used to calculate the data range to record it. It doesn't magically remove the other elements because it says manganese 2p. So you have to check if there's other things there. Especially important when working with trace components. So if you're looking for a very tiny amount of a dopant, for example, and you scan 300 times in a particular region, there could be a very tiny core line from another element, maybe one of your main constituents of your sample, and that will show up in that region. So it's really important to make sure if you're looking at trace analysis. Not understanding multiplet splitting. Okay, this is number one, or in terms of the places where people fall down. So I think we've seen earlier on that multiplet splitting is a phenomenon that we get, especially in tertiary transition metals, and some other places in the periodic table as well, mostly tertiary transition metals, which makes their spectra incredibly complicated, even when we only have a single chemical environment or a single oxidation state. So some examples of standards here. So the one on the left is kind of at least the data or the effort to report data is good. So, for example, here we have some cobalt peaks. So, different cobalt compounds, for example, cobalt monoxide, O, so cobalt 2+. This is probably reasonably pure cobalt 2+. But if you look at the peak shape, it looks very complicated. So, if you come at this from a point of not understanding or not having really worked with multiplet splitting before, you might think this is a mixture of lots of different cobalt oxidation states, and that may be what you expect for your material with cobalt. And like many transition metals, it adopts lots of oxidation states. So cobalt oxide here, we have the metal below, which again has a reasonably complicated shape. Cobalt hydroxide you see looks a little bit different to cobalt oxide, and then CO3O4, which is a mixture of cobalt oxidation states, of course, looks again a little bit different. But some people ignore all that stuff. Well, some people ignore that stuff. Can you help me with this? We're on slide 28. Thank you very much. Okay. Perfect. But some people ignore that stuff. So we can see some cobalt peaks in panel C down below, and they've not bothered with measuring any standards, not bothered looking up literature or any of that kind of stuff. They just fitted a 2+, a 3+, and stat, which you can just use for anything, just to hide the rest of the spectrum you don't understand. So they've come up with a 2+3+ ratio there. Also, a really weird outcome. Which I'm not sure how they've achieved. Not sure how they've achieved. But a 2+3+ ratio, which if you actually compare the cobalt 2p spectrum to the cobalt oxide, the cobalt monoxide, it looks pretty similar. So they may well just have really cobalt ratio plus there. Manganese, another same figure. This is the same figure. So we have a lot of work on this. The manganese up here again, 2+3+ fitted, no account taken of the multiplets fitting in manganese. So when fitting chlorides and multiplets, look up reputable papers that discuss the fitting in detail. So don't go to just the first one you see. Don't Google manganese 2p XPS and take the first image. Maybe how I got this one, I don't know. Find a paper which actually talks about this in detail, talks about the different ways to approach the fitting and the different way to do it. It might not agree with this is the best way, the way they fitted it, but they have made an effort to do it. Know that multiple structure will depend on the coordination environment in that, so that's really important. And I think, as we spoke about earlier, multiple fitting comes from transitions in the valence orbitals. So the energies of the valence orbitals will be dependent on the coordination environment metal. So the hydroxide will be different to the oxide, will be different to halides. So these are kind of additional layers of complexity. Consider using standards. It's as shown on the left-hand side, I think it's really valuable. Try trend analysis. So, for example, your research question is to understand the transition metal oxidation state, how the average oxidation state changes. Can you do a trend analysis with samples where you do successively more of whatever you're doing? So heating it up or adding the gradient, whatever it is, so that you can see how it changes over a series of samples. That can give you much more robust analysis than just looking at one sample. Say I'm going to fit this one sample from scratch. You can show how the spectrum changes over as a function of some treatment. That's a much more, I think, robust way to do it. Sometimes it's not possible to do it. So FE2 plus FE3 plus is extremely difficult, unless you can use another outside source of information or do something like this trend analysis. So it might just not be possible to get a reliable answer. Okay, number 9, forgetting to fit the model. So we don't need to say too much here. They had 3 components and exported the data straight away. Using quite a nice graphing program. Without pressing fit, sad. Just keep adding components. It's reasonably common. So if you want a better fit, you want more components. Guaranteed 100% success rate. More components equals better fit. Mathematically, of course. Mathematically, you will have a better goodness of temperature, but we fall down on physical interpretation. So here we have some carbon. I mean, these are all carbon. Huge area, all of the carbon. So I can't even count how many components there are there, but there's a lot of them. What I will say, background looks good. All of our maximum of them is reasonably similar. That's it. But there's many ways you could fit, different components for that spectrum. No unique fitting you can get. So it's very difficult to pull out information. There may well be, as I said before, other extra information you can provide from other things, especially in organic materials. That's often a possibility. But in this case, I think we're a bit past that. So when adding components to a fit, consider what the physical meaning of that component is. Don't add more peaks that can be justified. Either by arguments by what the forward maximum should be, again, maybe based on some standards, or from outside information like the structure of the polymer, for example, or any other information. So again, additional information, extra structure polymer may justify more conflict. If you're only fitting like that, that's your only information. There's an infinite number of models. Bonus round. Okay, so this is we can do audience participation. So this is I actually said I found this bill. I sent this on our WhatsApp group. I said, is this the worst ever published XPS spectrum? Or XPS figure? Does anyone want to comment, critique? There's lots here.
What's the dark blue one?
So what's the dark?
The dark blue one. I can't read it.
The dark up here.
Yeah.
So the texture says some. So the black is the sun, and we have cesium 3D 502 and cesium 3D 302. So the 502 is the red one, and the 302 is the blue one. I hope that's what it is.
Yeah.
Okay, there's a really obvious one.
No experiment.
Backgrounds are wrong.
Yeah, the backgrounds are awful. So backgrounds here. Yeah, this is bad. This I don't even know how it's possible. If you had a shadow background, it will finish where the data is. So I don't know. I mean, it's impressive.
Maybe data data rather than the program, so there was some features that you showed off it that affected the background. Maybe it's gonna.
Josie's very experienced at this kind of. Yeah, that's exactly that. Could definitely be what's happening. That could definitely be what's and again, so every single one is for all four bad. So this one, really bad. Yeah, so maybe it's this. I think you're right. It's similar to this, but they cut it off. They thought it looked bad, but not indeed. Background is one. Yeah. Anything else?
There's a broken 3D 1/2 there.
Yeah. So they invented new quantum physics. High impact labels. But yeah, maybe not for the best reason in this case. So bromine 3D, one of those. So they had, you can see their motivation. They looked at the spectrum. They thought, why are there three peaks? Well, we know we have the 502. We know we have the 302. So it's obvious. The next one is 102. So they've done. No, it's not. You only ever get. Because you're only removing one electron from the field orbital. There's only two ways that the spin of that whole of the can be. So there's not three ways to go. So unfortunately, that is incorrect. But there's another thing related to that. So on D, this is probably too high. I think for what's going on with D? Remember?
I don't know what else going on with D. Why have we got a shoulder on the 71st?
Yes. Oh, no. That's the bromine. So the bromine, they didn't look up the splitting between the bromine 3D spin orbit doublet. This thing here, sorry, audience mine. This thing here is actually all of the bromine 3D. But they're so close together, the splitting is very small, so it's just a shoulder on the side. So this is actually a cesium peak. This is cesium 4P, I think, something like that. I might be wrong. It's definitely a cesium peak. So what they've done, they've again misidentified a bromine people. They haven't realized that features from another element may appear in their region even though it's their bromine 3D. They figure it. I think there may be some those on. This one's actually a little bit harder. I think this is mostly around. Should have done this first because then you're on scrolls. Again, they have 3/2 and 1/2 the wrong way around. Intensity, probably not too bad. Again, they have this is the one figure as well, which I thought was this. They have manganese 3, manganese 4 plus, 50 small plus 15 completely wrong. Again, down here as well, so 2 plus. And now we have the 3/2, the potassium 2p 3/2, 2p 1/2. Different widths and completely wrong intensity ratio, and still, oh no, they're the right way around. Everything else is wrong. So that was it. Another one. Okay, so we've had a lot of tips for kind of better XPS on each stage. But I'll try to make some of them here and do an overview. So I think something that can improve a lot of XPS practice, especially for people who come to is to design your XPS experiment carefully. Don't just kind of shove it in and say, okay, I want these elements, I want to know about these elements, and then I'll worry about the analysis afterwards. Think about how you're going to do the analysis. Think about what your research question is before you actually go to the spectrum which then record the data sets. That way you'll think about, do I need to record any samples? Do I need to worry about overlapping peaks? do I need to do something like a trend analysis? Do I need to send, instead of just one sample, do I need to send, a blank sample with no joke, or samples with varying levels of joke, so that I can see how, what progressive changes are expecting, that could give you much more information. Collect good quality data over an appropriate range. So often the kind of default range that comes with the spectrometers might not be wide, especially for elements which have a very kind of large range of chemical shifts for different elements. So be critical of that. Think, I can just collect sort of a wider range. It's almost never wrong to do that as you go lazy and collect 1,000 EV. But just add a few EV to each side, and you'll probably have data which much easier to analyze. Be aware of important feature phenomena and how to deal with them. So the main two, as I said, spin orbit coupling and multiplet splitting. So multiplet splitting might not apply to everyone, although for catalytic material, I think it's going to be very common. Spin orbit coupling is much more common unless you're kind of an organic person and you just deal with first row elements. Know how to deal with these, and don't, and I guess the last point, consult reliable literature. So much of the published XPS is wrong, and unlike in Simon's case, the case that Simon showed, they don't always kind of feel embarrassed enough to put it in the SI. It's often just front and center. I think referees generally do a really bad job, especially in papers where XPS is one part of a much wider analysis, and those tend to be the papers that get in the really high impact journals. So if you look in Nature Materials, Matter, all those, any other journals where you get very, very high impact studies, they often will have many, many different techniques. And so, the referees might really not know anything about XPS. They know about batteries, they know about catalysis, they know about something else. So they might just wade through the XPS. Unfortunately, that means, I would say, probably the impact factor of the journal, the one use of the impact factor of the journal is that it's kind of inversely correlated with how the XPS is studied. So we have found a use for the journal. Yeah, so consult literature that actually discusses the fitting of these ingredients. I'm not just showing one spectrum with a couple of ingredients, and that's it, even if it's in a great journal. So resources, you guys already know about HarwellXPS Guru. This is a really good knowledge base that's been put together by the guys here at HarwellXPS, plus I think some other people. There's a forum there, you can ask questions. There is a, sorry, I pasted over that. There's a whole load of videos that are mostly markers, I think, covering a whole massive range of different analytical methods, going through all of this in a lot more detail than I have here. And you can ask questions on the forum as well. The paper that I was speaking about right at the beginning is the last one here, affecting the frequency and nature of erroneous X-ray photoelectron spectroscopy analysis. So that doesn't really tell you how to do it well, which just tells you how bad everyone else has done it. But the two above that are quite good. So practical guide for curve fitting, X-ray photoelectron spectroscopy, the top one, the use of issues of curve fitting, and the analysis of X-ray photoelectron data. Good references. There's lots of others as well. These are up-to-date ones. There's textbooks and things like that. Or get in contact with us at HarwellXPS. We're always really happy to have a look at your spectra, and say what we think is good, what we think is less good. So I'm going to wrap up there. Very happy to take questions. Thanks very much for your attention.
Any questions?
Let's go back to the second section, because I think I missed the last point.
Can you speak up a little?
So number two, was that?
Yeah, the last point.
I think it was in the background.
It's like this is
This part. Oh, sorry. So this is fitting symmetric peaks, or attempting to fit symmetric peaks. Is this what you mean?
yeah, the last point of this slide.
Okay. Yeah, so I just need to acknowledge, you might need to acknowledge that you can't get to a single answer. depending on it. If all you have is a symmetric peak and you don't have any other information, you know, there's an infinite number of models of two things or more things you could fit that. So you might not be able to give a final answer. That might not be what the PI wants to hear.
Also, it may be silly to ask, but is there any like database for the standard half-life?
So some of the databases do include that. I think the important thing is that it will vary by instrument. So different instruments will give you different forward maximum because part of the breadth of the peak is due to instrumental run. So it will depend on, for example, the pass energy you run at, or you know, how good your electronics are, or whether you have monochromatic X-rays or not, or most systems do that. So I think in this database does have forward maximum data, I think. Although I never really looked at it. So the NIST database does have, I think, forward maximum data. But to be honest, you really need to look at your own system, whatever system you're in. So that's why I think doing things like measuring standards is really important.
When you talk about errors in spin orbit splitting, you start with silicon, which is an interesting case, right? Because when you oxidize silicon, the spin orbit splitting appears to disappear, right? Because elemental silicon, you see it with the resolution high enough, but for oxidized silicon, you get a very symmetric peak that's very often, almost 100% of the time, fitted by ignoring spin orbit splitting.
Yeah, exactly right.
Would you consider it acceptable for fitting the silicon oxide peak?
Depends what you want to do. If you want to know the ratio of elemental silicon to oxide silicon, yeah, sure. You just need to know the area. You need to know the area of the oxide peak versus the area of the elemental silicon. So, for example, classic use of that is to get the thickness of the SiO2 layer. You get it by measuring the attenuation of the metallics of the elemental silicon. So in that case, you just need to know the area.
Right, but then you would just integrate it. But I mean, so let's suppose you do want to fit it for some reason. Would you consider fitting the silicon oxide peak with a symmetric peak?
So if you want to pick up different environments of silicon, different chemical environments of silicon, you mean, for example?
Yeah.
You probably could get away with it. But those different. I don't know whether silicon halides would come. I don't know whether done silicon. Has anyone done silicon halides? I think what would be significantly different to the oxide? Maybe silicon carbide. Yeah. What do you think? What would you use? A single environment, a single peak? Sorry. I probably don't know. Yeah, I probably always put the two components on there. I think is probably the best.
I would do the same, but then you also add more peaks, right? Of which you don't really know the location.
No, but they're constrained. You know the spin. You can constrain the separation, constrain the shape to be the
Yeah,
same.
but you would probably
you already
more
you already
duplets.
have one component, really.
Oh yeah,
Completely constrained.
but you need to end up with a symmetric peak, right? So you need at least several duplets to get a symmetric peak.
Well, I think it's almost symmetric. I think the spin orbit coupling is still there. Yeah.
It should be there, right?
Yeah, it definitely is. So it's definitely, you know, it's not. It can't be completely symmetric. It may be symmetric within the error of the mission. I would say fit it with a spin orbit coupler.
I have a question online, which is about the doublet peak of bismuth
Yeah.
that you can demonstrate. Is it possible to treat each peak as a single peak? I mean, while considering the start and end of the peak.
Absolutely. So if you want to, I think if they mean setting up regions. So if you want to model it as two different regions, yes, exactly right. Yeah. So I think that's probably the best approach. So if they use a linear background, it can be fine. Yeah, probably the best approach is to have two different regions, and then you avoid the background problems in the middle. That's what I mean. That's a good approach.
I think we had a couple of questions in the room, and then we had one online. So I have another question from Tony, and then we'll put one online.
So I guess my question is really particularly seeing with column 1, I have arguments with polymer colleagues of XPS fitting on a similar line, but we don't have and some of this is our instrument resolution varies a lot and so on, but we don't have hard and fast rules on information content. If you practice XRD or you do XAPS fitting or something, your software tells you when you're exceeding that information content. To some extent, is it sort of a community problem that we don't build that into our software to try and tell us when we are overfitting the data? Because
Yeah, I think that's a really good contrast with those other methodologies. So in diffraction or in fitting like exo absorption data, which many people may do regularly here. In those fittings, you're in most cases you do something like rebound requirement, for example, powder reflection pattern. You start off with some atomistic model. So you start off with a physical model of the unicellular crystal, and then you calculate the expected diffraction there, and then these parameters you can change. But you're fitting kind of a large number of peaks at the same time based on an atomistic model. So unfortunately, we don't have that, or certainly that hasn't been developed for XPS. There may be some ways kind of into that, but I don't think there's much progress made towards that. In XPS, we tend to, actually this is the point I could have made as well, it can often be very helpful to look at different regions of your spectrum, not in isolation, to fit them kind of independently. For example, if you have an organic species where you have a carbon peaking fit, a carboxyl environment, what about the oxygen? Do you see a similar amount of oxygen to account for that carboxyl? Is that to the things to tally together? So I think in things like root refinement and XS analysis, because we have that atomistic model, we're much more constrained on what we can actually, the models we can actually make. On XPS, on XPS fitting, if we focus on one region, how far can we change? Pretty much anything. There's no underlying atomistic model that will say, well, that doesn't make any sense to the Brax or because of whatever what governs XPS. So it just doesn't work. I don't know if that's the kind of thing you're actually thinking of.
So I guess there's still an information content argument, but it's complicated by whether you've got standards or not there, so you know what because you're not, your resolution, we measure points in XPS that are much tighter resolution.
Yes. Well, I guess it's the same thing in most power bands. Most power bands, you have many points across the reflection. So your total number of observations is normally very high. So the theoretical number of parameters you could refine against that is whether that equation is the number of observations, but realistically you will want to refine far fewer than that. I think because you're limited by that kind of model, but XS with it, maybe not.
Tony, I think you had a
Yeah, it was kind of going on the same way. I was going to ask if for XPS analysis we have the option of doing principal component analysis first to see how many peaks we have. Is there any equivalent thing in XPS analysis?
You can do principal component analysis, and that can be very helpful. So that's kind of course you need some kind of some series of data where you can kind of try to extract that. But that can be very powerful methodology, especially for using things like event spans, which I didn't talk at all about. Understanding event spans in event spans can be very difficult, but PCA can be a way to do that if you have a series of samples where you're changing something. So yeah, you can definitely do that. I think the CAT implement lots of incident on target patterns. So it's quite easy to do that, especially now on charge if I'm more interested in that. It's very, very easy to do.
we have one last one online, which I think is quick. There was a question about the 3 DR peaks, but I think you noted that was an error on behalf of the authors rather than an actual.
All of these, yeah, all of them. That's the theme of the talk.
Yeah. The question was, how do you differentiate between noise and satellite or shape-off peaks?
Okay, so the noise is if you measure a region of the spectrum where there isn't any recognition feature or there is any special feature. So, you know, if you, this measuring a wide range will give you ample regions where there's noise. And if your feature is the same size as the noise,
So,
might
yes, I think that's about all the time we have time for. We have run over, but it just goes to show how valuable today's been with the breadth of questions. You do have further questions, please do get in contact with HarwellXPS. I'm sure they will be happy to discuss things or help sort of after the end of today's session. I hope you'll join me in thanking all of today's speakers. Karine and Mark doing all the hard work in the organisation. It was just my bright idea and then they did all the work. And so yeah, thank everybody.
I'll just echo that. Thank you very much everybody who's taken part. And the one point I want to make, to get to Rob's sort of there, is that even if you don't do XPS yourself, you are now all ambassadors to help us improve the state of everything else in the world, because you will all be refereeing papers in the future. And I want you to promise me that you look at the XPS data, even in a science paper, and make sure that it's been done properly.
So imagine if there is a paper, I don't know if Rob has done it. Have you written back to the editor saying that, okay, is it like improper in using these things?
Yeah, absolutely. You
Yeah.
can send it back to them and say these be embarrassed. to
Or
send
which
it
have been
back.
published at home.
Yeah, absolutely. So thanks again to the people who did all the hard work and all the speakers, and good evening.